On this slide, we review the concept of pure bending and the neutral axis of a beam. First, let us recall what we mean by pure bending. Pure bending occurs when a beam is subjected to a constant bending moment with no shear force. In this condition, the stress distribution across the cross-section becomes very simple and very important. As shown here, the normal stress in the beam varies linearly like this with the distance y from the neutral axis. Y is taken from the neutral axis, just like this figure. The part above the neutral axis experience compression, while the part below experience tension, or vice versa, depending on the bending direction. The slope of this linear stress distribution depends on two key factors: the applied bending moment, the second moment of area, also called the moment of inertia, I. Okay, this is defined to be I, moment of inertia. The relationship is fundamental and leads directly to the bending stress formula that you have already studied. Understanding where the neutral axis is located is therefore essential for predicting maximum stress and ensuring safe design. This slide introduces the concept of the section modulus, which is a very practical design parameter. The section modulus is defined as the moment of inertia divided by the distance from the neutral axis to the extreme fiber, just like this. Physically, the section modulus tells us how efficiently a cross-section resists bending stress. For a given bending moment, a larger section modulus means a smaller maximum stress. From a design perspective, engineers often compare different cross-sectional shapes using section modulus rather than the moment of inertia alone. Why? Because failure usually occurs at the outermost fiber where the stress is maximum. So, when selecting beam shapes in real structures, bridges, frames, machine components, the section modulus becomes a key indicator of strength against bending. Here we focus on how to determine the location of the neutral axis under pure bending. In pure bending, the neutral axis always passes through the centroid of the cross-section. Here. This result comes directly from equilibrium of internal forces. The compressive force must balance the tensile force. Mathematically, this means the first moment of area about the neutral axis is 0. This is a very powerful result. Once you know the centroid of a cross-section, you automatically know the position of the neutral axis as long as the material is homogeneous and the bending is pure. Later, when we deal with composite materials or unsymmetrical sections, this assumption may no longer hold, but for now, this principle greatly simplifies analysis. From this slide, we introduce the idea that beam performance strongly depends on cross-sectional shape. Even if two beams have the same area, let us consider the case two beams have the same area, their bending behavior can be very different. Why? Because what matters is not just how much material we use, but where that material is located relative to the neutral axis. Placing more material farther away from the neutral axis increases the moment of inertia and reduces bending stress. This idea explains why many structural beams do not have solid rectangular shapes, but instead use shapes such as I sections or box sections. This slide connects geometry with material behavior. At the very top, the key sentence says the maximum tensile or compressive stress is proportional to the distance from the neutral axis, just like this, to the most remote fibers. That statement is basically the bending stress idea. The farther a fiber is from the neutral axis, the larger the stress is experienced. The first case, material with the same strengths in tension and compression. Look at the fiber bullet and the three sketches: rectangle, circle, and I shape. In each sketch, the centroid is in the middle of the depths. So the neutral axis passes through the center line. That means the extreme fiber distances in tension and compression are equal. In other words, if the material is equally strong in tension and compression, it is fair to place the neutral axis in the middle so that the maximum tensile stress and maximum compressive stress have the same magnitude, just opposite signs. The second case, the material weak in tension but strong in compression. Now, look at the second bullet. Look at this. And the trapezoid-like cross-section, this, on the right. Here, the total depth is labeled H. Total depth is H. The centroid is marked C, and the neutral axis is the horizontal line through C. Two distances are explicitly shown, C1 and C2. C1 is the distance from the neutral axis to the lower extreme fiber, and C2, the distance from the neutral axis to the upper extreme fiber. The important concept is we may intentionally choose a shape where C1 is not equal to C2. C1 is not equal to C2. If the material is weak in tension, we want the tensile side extreme distance to be smaller so that tensile stress is reduced. Because bending stress scales as sigma proportional to y, reducing the tensile side distance reduces the maximum tensile stress. So, on this slide, the message is a centroid location is not only geometry, it becomes a design choice once material tension or compression strengths are different. This is the design philosophy behind concrete members. Concrete is strong in compression, weak in tension, so we try to avoid large tensile stresses in the concrete, and instead we use reinforcement on the tension side. So I would like to leave a question. If the bending moment is fixed, which would you rather reduce, C1 or C2, to protect a weak in tension material, and why? This slide adds an engineering reality check. Strength is not the only requirement. Economy, weight and cost matters too. At the top sentence, if two cross-sections have the same section modulus, they provide the same bending strength for the same allowable stress. Then the one with smaller area A is more economical, less material, lower weight. Look at the rectangle sketch. Width is B, depth and height is H, and centroid is marked C at the mid-depth. Distances from the centroid to top and bottom are h/2 and h/2. Now the formulas shown are the standard results. Moment of inertia about the centroid neutral axis is I equals bh cube over 12. The section modulus to the top and bottom, because symmetric, Z1 equals Z2 equals I divided by h/2 makes BH squared over 6. That is the same as 1/6 times AH, because A denotes cross-sectional area, A equals BH. Because I includes H cube, look at this, I includes H cube, making a beam deeper increases bending stiffness and reduces stress very effectively. That is why deep beams and I sections exist. Put material far from the neutral axis. At the bottom, the slide warns if the rectangle becomes too narrow and tall, we get lateral instability, sidewise buckling. So even if bending stress looks greater on paper, the beam may fail by twisting or buckling sideways. This is a nice engineering ethics moment. A beam can be strong in the equation and still fail in real life. Okay. This page is a clean demonstration that shape matters even when area is the same. Look at this circular cross section. The circle has diameter d. The section modulus is shown as z equals pi d cube over 32. That is the same as 1/8 times AD equals 0.125 AD. 0.125 AD for the circular cross section. So for a circle, the section modulus scales with AD. Okay. Next, let us consider this square cross section having the same area condition. So the area of this square is the same as that of the circular cross section. The square has side length h. The same area condition is written as pi times d over 2 squared equals h squared. Therefore, h is determined as d square root of pi over 2. Then, using the rectangle formula with b equals h, we have the section modulus z equals bh squared over 6 equals 1 over 6 times ah equals h is converted to d, so 1 over 6 times a times 1.772 over 2 times d makes 0.147 AD. Since 0.147 AD is greater than 0.125 AD, the square has a larger section modulus. So square has a larger section modulus. So for the same bending moment, sigma max, sigma max equals the moment over the section modulus. Therefore, square produces a smaller maximum stress than the circle. Let us consider the interpretation of the above result. The square places more area farther. Square places more area farther from the neutral axis, especially near corners. So the practical takeaway is equal area does not mean equal bending performance. I would like to ask a quick check question. Which do you think is stronger in bending, a circle or a square of the same area? Why does the math disagree with our intuition sometimes? This slide is the design philosophy slide. Let us discuss the section modulus of the ideal I-section beam. Let's recall that when the section modulus is larger, we have smaller maximum stress. We would like to check how the section modulus of the ideal I-section beam is like. The principle we have to think is moving material away from the neutral axis. The text says, for economical design, most materials should be placed as far as possible from the neutral axis. That's because in bending, the middle region near the neutral axis carries low normal stress, while the outer fibers carry the highest stress. Look at this idealized pictures. There's no material near the centroid, neutral axis. The total area is divided into A over 2 at the top and A over 2 at the bottom. The distance from the neutral axis Z to each area is h over 2. The inertia is computed in a simplified way. I equals 2 times A over 2 times h over 2 squared makes 1 over 4 AH squared, and the section modulus is obtained by dividing I with respect to h over 2, making 1 over 2 times AH. So this ideal section is very efficient, large Z, large section modulus for a given area. But in the case of standard I-section beam, and that is a practical case, real beams cannot be just two plates, okay, like this. We need a web to connect this and this for shear transfer and manufacturing. That web adds area closer to the neutral axis, which is not as efficient for bending stress. So the slide shows a lower efficiency. Z equals 1 over 3 times AH compared to 1 over 2 AH for the theoretical ideal. So we can say engineering design is the art of approaching the theoretical best while still being manufacturable and stable. This example uses a triangular cross-section. In the figure, base width is B, height is H, centroid is marked G, the neutral axis is the horizontal axis labeled Z. Okay. Distance from the neutral axis to the top and bottom fibers are E1 and E2. Questions are: answer the position of the neutral axis. In order to do that, you have to calculate the centroid for triangle. Okay. The second question: what is the ratio of the maximum stress and the minimum stress? Absolute values. Okay. So let us consider the first question, position of the neutral axis. For triangle, the centroid lies at E1 equals 2h over 3 and E2 equals h over 2. Okay. You connect in order to catch the position of the centroid, you have to draw a line to the middle point of one edge from the diagonal corner, this, and also you draw another line to the center from A, okay, and you have the centroid from the crossing point of these two lines, just like this. All right. Ratio, the second question is ratio of maximum to minimum stress. The bending stress formula is this: sigma equals my over iz, sorry, z is missing. So the extreme stresses become sigma x max equals me1, E1 is larger, so me1 over iz, that is the maximum stress, and the minimum stress is minus sign of me2 over I2. Then the magnitude ratio is ratio R equals sigma max over sigma min to find E1 over E2. By substituting the values E1 and E2 into this expression, we obtain R equals 2. So the stress at the apex side is twice the magnitude of the stress at the base side in absolute value, because the apex is farther from the neutral axis. Even if the cross-section is simple, asymmetry in distances E1 and E2 produces asymmetric maximum stresses. The title of the slide from this page is Deflection of Beams. So this page is a clean transition. We shift from stress to deflection. I would tell, even if your beam never yields, you can still fail the design if it deflects too much. Doors won't close, machines lose precision, bridges feel unsafe. So from here, bending stress checks strength, deflection checks serviceability. Both are required in engineering. This slide defines the elastic line, that is deflection curve. The key equation is shown here. 1 over rho equals m over ei. Rho is the radius of curvature, so 1 over rho is the curvature, m is the bending moment, and E is Young's modulus, and I is moment of inertia. If m is constant, E and I are also constant, so 1 over rho, the curvature is constant too. So the beam bends into a circular arc. In general, beams under transverse loading m varies along the length, so curvature varies. In general beams, the curvature varies. The deflection curve changes shape. This is the bridge idea. Moment diagram to curvature distribution to deflection curve. All right? Moment diagram, you are able to draw the moment diagram. Then M has a distribution, so you have the curvature distribution. Okay, so once you have the curvature distribution, mathematically you are able to obtain the deflection curve, and it is shown from the next slide. This slide begins with the exact mathematical curvature formula. This, when y, that is the displacement deflection value, y is a function of x. Okay, this is a very mathematical expression. So the curvature includes in the numerator the second derivative of the deflection, y, and in the in the denominator it has the slope, the first derivative of the deflection, as you see here. Then it states, assume deflection is small. Okay, deflection is small. That means dy dx, absolute value of dy dx, is much smaller than 1. Okay, you are comparing 1 with this term, okay, square of the deflection. And if the slope dy dx, first derivative of y, is much smaller than y, then you are able to replace the denominator with 1. Okay, so you obtain, as a result, you obtain this. 1 over rho equals minus sign of the second derivative of the deflection. Now combine with the bending curvature relations. 1 over rho equals m over ei. So you have the standard beam equation. The second derivative of the deflection equals minus sine of m over ei. You have to memorize this. The diagram on the right, this helps interpret symbols. Okay, take a look at this to understand the symbols of these equations. All right, x is the coordinate axis, y is deflection. Y is taken in the vertical direction from x axis, and theta is a slope angle. Theta is a slope angle. So if you move a little bit from the original position, then theta changes a little bit. ds is the arc length. d theta is the change in slope. Rho is the curvature radius. Rho is the radius of curvature. Okay, to understand this and this and this, you have to look at this diagram. So we find the deflection is a calculus problem once you know the moment m as a function of x, m of x. This is a simple differential equation. This page fills in the geometry. It states the arc relation ds equals rho, this is a radius of curvature, times d theta, that is a change in angle. So d theta ds equals 1 over rho. Therefore, d theta ds is related to d theta ds is related to y, because theta equals dy. Approximately, theta is dy dx. So we obtain this. So combining A and C, we obtain this, right? This is a simple interpretation. The sign, plus and minus, depends on the coordinate convention for positive moment and positive curvature. Let's see an example now. This example is the classic simply supported beam, AB, with a uniform distributed load, W, per unit length. In the figure, supports are at A and B. This means the beam is simply supported. Span length is L. Distributed load intensity W per unit length. Coordinate X measured from A. Okay. Deflection Y of X is downward. Slope at A leveled theta A. Maximum deflection at midspan leveled delta. Symmetry shows midspan is at L over 2. The problem asks, develop the equation of the elastic line deflection curve and find maximum deflection delta at midspan. That's the question. Now we write the bending moment at point X. The slide gives mx equals wl over 2 times x minus wx squared over 2. Okay? This is a very simple example to obtain the moment, bending moment. All right. The reaction at A is WL over 2 by symmetry. So moment from reaction is WL over 2 times X at X. Okay, at X, the moment becomes WL over 2 times X. All right, this is the moment from distributed load over length X. Okay, you have to calculate the moment from the distributed load from A to X as well. So the moment from distributed load can be replaced with the force at x over 2 with the magnitude Wx. Okay, so it gives this moment, Wx squared over 2, right, in the opposite direction. So the total amount of moment becomes like this. All right. Then we plug into the differential equation EI, and second derivative of y with respect to x equals this. Okay. You need minus sign of the right hand side to have this. Okay. By integrating this both sides with respect to x once, we obtain this expression with the integration constant cy. And cy should be determined by considering some geometrical condition. Now, let's use the condition used in symmetry. At the center, L over 2, the slope should be 0. Therefore, dy dx equals 0 at x equals L over 2. By substituting this value into this, you obtain this. C1 equals W L cube over 24. So the slope equation becomes this. Okay. And because this is the slope equation, and on the left-hand side, you still have the derivative of the deflection. So in order to have the deflection itself, you have to integrate this one more time. In order to have the deflection expression, we have to integrate the slope equation again, just like this. But again, we have an integration constant, C2. Now, we use the support boundary condition at A, that is the left end, to determine C2. Left end is the place point corresponding to x equals 0. X equals 0. So, substituting 0 into this expression, you obtain C2 equals 0 as well. Okay. Then the elastic line equation becomes this. And finally, deflection occurs at midspan, x equals L over 2. So substituting x equals L over 2 into this expression, we obtain the deflection y of x at x equals L over 2 at the midspan, that is the delta, deflection at the midspan. 5 W L to the 4th over 384 EI. This is a major memorize-worthy result, but more importantly, you should understand the structure. First, find the bending moment as a function of x, and integrate twice, integrate 2 times, and use boundary conditions, symmetry, or the condition at both ends. Okay. In this case, the problem was symmetric. Therefore, we are able to use the condition at the midpoint, midspan. Okay. That is the flow of solving the deflection of beam problems.